Suppose we wanted to find the slope of the tangent line to the curve x squared plus y squared equals 25 at the point 4, 3. So notice what this is asking. Right, this is the equation of a circle with a radius of 5. Right, so roughly looks something like this. And we want to find the slope roughly of that line, if that's the point 4, 3. Right, rough sketch. Well, an option is to solve the equation for y. So y squared equals negative x squared plus 25. Then we can take the square root of both sides. Y equals plus or minus the square root of negative x squared plus 25. And we could attempt to take the derivative of y. But the problem is going to be the plus or minus for us. Which one should we be thinking about? And there may be some ways to make that decision, but it's going to be better to use a different technique. Because sometimes you'll have equations like this: x squared plus y cubed plus y equals 2, where it's going to be difficult and maybe impossible to solve this equation for y. So we need to use a different technique, and the name of this technique is implicit differentiation. What you've been doing is explicit differentiation. So now we're just using a different technique. Let's consider our initial problem, but this time we'll solve it using the technique of implicit differentiation. So instead of solving for y, we're going to take the derivative of each piece. And in this case, we're going to take the derivative of each piece with respect to x. So let's do this in a lot of detail. The derivative of x squared is 2x, and the derivative of y squared is 2y, and the derivative of 25 is 0. Now, some important things. We've taken the derivative of both x and y, and we've done it with respect to x in both cases. So some notation that we're, in a sense, always using but never have needed before. When we took the derivative of x squared, we took the derivative of x with respect to x. And when we took the derivative of y squared, we took the derivative of y with respect to x. And when we took the derivative of 0, we took the derivative of some constant, x, with respect to x. Is fine, even if we use dc dx, because 0 times anything is going to cancel this out. And notice that dx divided by dx, if you'd like to think about it that way, is equal to 1. So using all of that notation, which is important for implicit differentiation, we're left with 2x plus 2y times dy dx is equal to 0. Now, what we're interested in is the slope of the tangent line, which would be related to dy dx. So if we could solve this, or when we solve this for dy dx, we'll be able to answer the question. Subtracting 2x from both sides, we're left with 2y dy dx equals negative 2x. Dividing both sides by 2y, we find that dy dx is equal to negative x over y. And since we're looking specifically at the point 4, 3, then dy dx must be negative 4/3. Or the slope of the tangent line must be negative 4/3. And we've just used implicit differentiation to do this. Let's practice this a bunch to refine our technique. But ultimately, instead of solving for a variable and then taking the derivative, we're going to take the derivative of everything with respect to a single variable. when we're using what's called implicit differentiation. Example 1, we'd like to find dy dx for x squared minus y squared equals 16. We want to find the exact value of dy dx at 5, negative 3. So, by implicit differentiation, we will have 2x minus 2y dy dx. And the way I remember it is, with x squared I took the derivative of x, so I don't, with respect to x, so it's just going to cancel out. And with y squared I took the derivative of y with respect to x, so I need the dy dx there. And the derivative of 16 is 0. And 0 times anything will remain 0. Solving this for dy dx, we will end up with x over y. And specifically at the point 5, negative 3, dy dx must equal negative 5 thirds. Let's do another one. Let's find dy dx for the equation xy plus y equals 9. And we want to know dy dx specifically at the point 2, 3. When I take the derivative of x times y, I'll need to use the product rule. So it'll be 1, the derivative of x, times y, plus the derivative of y is 1 dy dx, and that needs to be multiplied by x. So I've just used the product rule on xy. Now I can take the derivative of y. And when I take the derivative of y, that'll be 1 dy dx, and that equals 0. I'm going to gather all my dy dx's on one side. So that means I will have x times dy dx plus 1 dy dx is equal to negative y. And to get dy dx alone, I'll need to factor it out. So dy dx times x plus 1 equals negative y. So dy dx equals negative y over x plus 1. And specifically at the point 2, 3 will equal negative 3 over 3, or negative 1.